There we go. So just as we get started here, here's our itinerary. Our first test will be 1 week from today. So next Wednesday, first test will be over whatever we've done in chapter 1. So we're going to finish up today, talking about logistic equations, and then probably a couple examples of solving by separation. And then on Tuesday, we'll finish up talking about solving exact equations. So that's our itinerary. So next Wednesday will be our first test, 1 week from today. Okay, let's try it. So if you recall, we left off, we were talking about the logistic equations. Logistic equation. And what we had said is we were just looking at the general form of y prime is ay minus by squared. And what we had said is we said that this first term gives us exponential growth, but the second term stops the growth. So we did that. Another way to look at that was if we factored out an ay, then we can write this as 1 minus b over ay. And then we went one step further, and we said we can write this as ay times 1 minus y over a over b. Okay, right like that. Just so you don't forget like which fraction goes where, I'll write it like this. That little fraction is in the bottom of the fraction. We have denominator of the fraction. And we call this a over b, so we said that a over b is carrying capacity. Okay. Another thing we said is, well, wait a minute, if this is growing and this is slowing, where is it growing to and where is it slowing down? So in other words, where are the steady states? So what we said is, we said our steady states are when y prime is 0. Y prime is 0. And the ideal equation form is probably to solve the second line here. So we solved that, and so we said that 0 is equal to a times y times 1 minus b over a y, and that gave us roots of y equals 0 and a over b. Oh, great. If it's not telling you, I'll change it. A over b. And we graphed it like this. We had a time was here, and we had our steady state, which is right here. This is a over b. And our graph was our steady state. Okay, there's one of them at a over b, and our other one is down here at 0. back at all. Another thing is, then the next thing what we did is we said, is if you start somewhere in this middle region, no, let me go back. Oh, what we did, if you look in your notes, is we graphed this. And what kind of a picture did we get if we graph this as far as our, you know what, I'm just going to write it, otherwise it's not going to make sense. So, let's graph that. Make a quick graph of, on your horizontal axis, y, and on your vertical axis, y prime. And we already know our roots. Our roots are 0. I'm going to put my roots up here in blue. My roots, or my zeros, are here and here. So this is A over B, and this is. And what we get is, what kind of a picture is that? It's a parabola, right? And is it going to go up or down? How do you know? Right, because we've got a negative b in front of the second degree term. Sure. And so what happens is we have a picture that looks about something like this. And I think about that's where we ended. It took us a lot longer, but that's where we ended. So then, we can use the knowledge of the derivative to graph the solution. Remember, this is just the graph of a derivative. So what that means is, if the derivative is below 0, meaning the values of the derivative are negative, what do you know about the solution in that region? It's decreasing, right? So our solution when you're to the left of 0 is going to be decreasing. What about your solution between A and B? What do you know about it? It's always positive, so this is an increasing solution. And what do you know about solutions that exceed A over B? They're decreasing solutions. So what we did is we said this. We said if you're below 0, you have a decreasing solution. And they actually drop off like immediately. It's almost not even worth graphing them. If you have, if you're in between A and B, well, what we said, for example, is you might have a picture that comes up, and then it bends back around. And it's always getting closer and closer to the steady state because it's an increasing function. Or the function is increasing in that interval. And then finally, if we start above A over B, then we have a decreasing function. So we get a solution like this. Now, there's a little bit more that we can discern from this. Let's find, notice this is a curve. If I was to look at this curve in this region, we would probably describe it as being concave up. If I look at it in this region, you would probably say it's left. Concave down. The question is where is the inflection point? Can we find that? Marceline?
I was wondering if it has any you said like it's 4-0 or like that section the graph. If it's at that dotted point was at the start, was switching from one to the other, was it there?
Oh, it's if your solution was A over B, or that was your function?
You dotted line right there on the y prime by y graph?
Oh, this one right here?
Yeah.
Oh, it's a parabola with a vertex. Remember, if you look back, we found that the vertex was always A over 2B.
Yeah, so the graph at the vertex is at all.
Hold on to that thought. Hold on to that thought. But back to this. How would you find the inflection point? Where would that be? It's when the second derivative is 0. And it's so nice, we don't even know the function, which is kind of funny when you think about it, but we do know the first derivative. So if you know the first derivative, it'd be pretty easy to find the second derivative. So I'd like everyone to take a minute, find the second derivative, set it to 0, and find your inflection point. So I'll write that while you're working is find the inflection point. Inflection point of y. I.e. y double prime is 0. Take a moment, solve that. I'm going to do it as well. So I'm going to come up with a minus 2b is 0. And let's see, subtract an a, divide by minus 2. What do you guys get? I forgot something? Oh, y, yes. Thank you. There we go. And, so we have y is equal to a over 2. Well, so look at that. That means our inflection point is half of this height. That's our inflection point. Wait a minute. Why aren't there other inflection points? How come there's none up here? It's always concave up. There's never an inflection point. Right. How come there's none down here? It's always concave down. That's right. Okay. I think we've done enough of that. Let's solve this problem. Let's solve it. No, you know what? Let's look at a problem and then we'll solve that. Oh, I have an idea. You move to a house. House on a lake. The lake has fish. In order to live, you're going to go to fish. These fish probably don't like it though. I mean, these are aggressive looking fish. They really don't want to be eaten. That's pretty good.
Yeah, that's good.
They're gonna bite you. Let's see how many can. So what we want to do is study harvesting of the fish. Fish in the lake. Alright, so let's try that. Here's what we do. We're going to start with no harvesting. Start with no harvesting. Okay, so let's do that. So I'm going to give you an equation. We're going to look at y prime equals, start with no harvesting. I'm going to put it this way, as described by y prime equals 4y minus y squared. Okay, let's try that. Yes?
If the secondary with the derivative left, it's not always guaranteed that it's inflection point.
Yeah, a flexion, I always have to look that up. Like, what's your concern? Maybe we can answer that.
What's that? I remember that having to check to see if it's an actual inflection point. Checking a point to the left and checking a point to the right.
Oh, you can do that.
Do you have to worry?
No. But you can. No, we don't have to. Right. Yeah, sometimes you have to check the interval, right? Or check like is it at y, is it y intermediate or not. All right. So let's do this. What's the carrying capacity of my lake? Well, let's find out. Find the carrying capacity. Find the carrying capacity of the lake. Okay, and what we do is we just factor. So we're going to write this as y prime equals, and I'm going to factor out this 4 and the y. So if I do that, I would bring 4y times 1 minus 1/4 y, is that right? No. Oh, I can never factor. I think that's, is that right? Yeah, that was it. But then, oh, here's what, remember how we wrote the carrying capacity? The carrying capacity was y over this fraction. So to put this fraction in the denominator, what do we do? We flip it and put it in the denominator. So we write 4y times 1 minus y over, well, 1/4 is reciprocal is 4. 4 fish. Or mean fish.